My name's Lee and welcome to Extra Maths. Today we're going to be dealing with your analytical geometry syllabus. And as you know, in grade 11 you did a whole lot of analytical geometry, but it didn't involve circles and tangents, which is exactly where we're going to start today. So let's start by introducing them and explaining where the formulas for them come from. Of course, your formula sheet does have these, well, two of these formulas. You'll see there's some stuff we need to know extra and above on that, but certainly some of it is given. So let's have a look. If we have a circle, you can see it's an interesting circle, but there you go. We have two possibilities. We could have the circle center the origin, which, believe it or not, is what I'm trying to do over there. And that means that I put my compass here, there, and I drew my circle like that. Now, this particular circle has the equation x squared plus y squared equals r squared. Now, you'll ask me, where does that come from? And really, that's easy enough to understand. If you think back to your trigonometry when you were working in quadrants, you were working with a theorem of Pythagoras. And this is exactly how we get the circle's equation. So let's have a look. We would draw a line from the center to any point on the circumference, which we know has the coordinates x, y, and we know that that's the radius. If we drop a perpendicular down here, we have y and we have x, and we can see from Pythagoras we are going to get the x squared plus the y squared equals the r squared. So that's really very easy. Another way to do it is to say this is the coordinate 0, 0. And so if we take this as OP, using distance formula, OP squared would equal x minus 0 all squared added to y minus 0 all squared, and OP being the radius is radius squared equals x squared plus y squared. Either way, we end up with this equation over here. Now, of course, we complicate this by moving the center off the origin. And to be honest, it mostly will be off the origin. Occasionally, you'll get a question with the center on the origin, but what makes this whole section interesting is the fact that this circle can move off the origin. So let's do that. Let's first clear this up a little bit. And let's lift our circle and move it so that its center is no longer at the origin. Let's make it about here. Now, what we would do is we would call this center now the coordinate AB. Now, if I'm looking at it again, I have a radius, and somewhere over here I have a coordinate on the circumference xy, which could be anywhere on the circumference. Let's call this C for center and P for point, very imaginative. And we can now say that PC squared is equal to x minus a all squared added to y minus b all squared. Now, PC is the radius, so it would be radius squared equals x minus a all squared added to y minus b all squared. Making it look a little bit more user-friendly, we could say x minus a all squared plus y minus b all squared equals r squared. Now, you'll remember when we did our revision of our grade 11 analytical, I actually did a mind map for you where I showed you on the one side what we had done, on the other side what we were still to do. Now, this would be a good time to refer back to that mind map and sort of bear in mind that we are now working through the other half of it. Right, now over here, as you can see, that's now the circle center, not the origin, and we got it just by using distance formula, so no big problem. Then the only other concept that we need to go back to is the concept of a tangent. So what I'm going to do is I'm going to take a circle. Let's just get hold of the circle again. Put it somewhere, it doesn't really matter where. And I'm going to put to that a tangent. Now, a tangent is a line drawn with one point of contact. So there we have it. This is the tangent. Now, what is important about this tangent is we are going to use some basic geometry, Euclidean geometry, to make sense of this. And the most important thing is the theorem we would have learnt if you were doing paper 3 that goes as follows. It says if we've got a circle and we draw a tangent to the circle, okay, And we then draw a line from the center to the point of contact of this tangent. Then this would be a right angle. In other words, the gradient of the radius and the gradient of the tangent are related to each other by using that formula for perpendicular lines, that the gradient of the tangent times the gradient of the radius will equal -1. This is a very important result, and we're going to get to use it a great deal while we work through the questions here in this section. Right, let's have a look at some examples and see how they are going to use these formulas. The first question says the equation of a circle is given by the equation x squared plus y squared minus 6x minus 3y equals 8. Now at this stage you're thinking, hang on a moment, that doesn't look like either of my formulas I've had. Remembering that the one formula read x squared plus y squared is r squared, and the other one reads x minus a all squared plus y minus b all squared equals r squared. Well, in actual fact, what you're about to do is discover why they dragged you through the section completing the square in grade 11, and why it is now extremely useful to you to actually sort the circle out, because the question says calculate the center of the circle. Now remember, the center is the coordinate AB. So if I can change this format so that it's written like this, I can just read it off, and the radius of course would come straight from that if I square root it. So in actual fact, what we're going to do is we're going to use completing the square. So let's go down a little bit so that we can get some space to work, and let's write this question down. It's x squared plus y squared minus 6x minus 3y equals 8. Now remember, the object is to get it into this format. Right, so what I would start with doing is getting my x's separated from my y's. So I would do that, and then I would go plus y squared minus 3y, and over here I would have my 8. So I've done nothing really at this stage. All I've done is reorganize my terms. Now, how do we complete the square? We take the coefficient of the x, we halve it, which is minus 3. We square it, which is 9. Now, some teachers teach you to write it like this. They say you go plus minus 3 squared. But of course, you've added this. This is a foreign thing. It wasn't part of the original. So we counteract it by adding minus 3 squared there. Then we go over here and we say, okay, fine, let's do the same here. Half of that is minus 3 over 2. Okay, so it'll be plus minus 3 over 2 squared. And again, this is a foreign thing. It wasn't there before. So we added this side, minus 3 over 2 squared. Right, so now we're ready to move on. Now, we have completed the square, believe it or not, and you'd say to yourself at this stage, hang on, this seems a lot easier than when we were in grade 11. And you're right, it is a lot easier than when you were in grade 11. First of all, in grade 11, you were solving for x, so it involved you working over the two sides to actually get an x value. And often you had very complicated values for your x squared coefficient. Now, this can happen. They could have had a 2, but the secret here is that your 2 would have had to appear on there and on there. So you could have divided through by it before you even started. So this is a much easier form. Now, this would come, and of course, you've completed the square there, so it's going to be x minus 3. So you'd square root this, and you'd square root that. Plus, and of course, that's a square. This one here, you're going to have y, because that's the square root of that, minus 3 over 2, and all squared there, equals. Now, of course, you're going to work this out. You're going to have 8 plus 9 over 4, because remember, you have to square these when you add them in. Right, so now this side is looking very promising indeed. You can see you've got something really nice looking at you there. And now we're going to say 8 plus, well, in fact, let's rather put it all over 4. It actually looks better. So it's going to be, that's over 1, so it'll be 32. And that's over 1, so it'll be plus 36 plus 9. So we have x minus 3 all squared plus y minus 3 over 2 squared equals, and if we add this lot up here, we are going to get 77 over 4. Let me just check I'm not telling you a fib. That's 68, 77. Yeah, that's perfect. So the center will be, remember how it worked? It was A, B. In other words, it had a different sign to what was written there. So this would be 3 over 2. And that would answer our first question. And our second question is the radius. Now remember, radius squared is 77 over 4, which means our radius is actually the root of 77 over 2. And yes, you could give your answer as a decimal, but remember, decimals are never really accurate. And so then you're sort of like rounding, and you should, strictly speaking, then say radius given to 2 decimal places. So rather don't. Rather just stick with your square root signs. There's absolutely nothing wrong with that. It's absolutely fine. Right, so now let me go back to what I was saying. I said to you some teachers would prefer you to do this. I would like to show you what I prefer to do. X squared minus 6x, leave a space, y squared minus 3y, leave a space, equals 8. So right, I would go across here. Let's change the color of our pen so you can see what I'm doing. I would take the coefficient of x, it's minus 6, halve it, it's going to be minus 3, square it, it's going to be 9, and I would put 9 on both sides. I take this, half of that is minus 3 over 2, square it, it's going to be 9 over 4, add it to both sides. So yes, the other way does help in a way because you know what the sign will be, but I think this is easy enough because now we know the first 3 must factorize to x minus 3 all squared, and these 3 must factorize to y minus 3 over 2 all squared, and then we would add this and the outcome would be the same. So I just found that an easier way to do it, and it seems to work for me. However, you must do what you're comfortable with. In the end, you want to make sure that you get the question right. And so it's all about what works for you. So I'm just giving you options and you can choose. So the first question, a little bit of interesting stuff, a bit of completing the square. Let's see what our second question brings. It says refer to the diagram. Given a circle with a diameter AB, with A the coordinate minus 2, 3, and B the coordinate 4, minus 7. So far that's just information. The first question says find the equation of the circle in the form x minus a all squared plus y minus b all squared equals r squared. Now, in order to find the equation of a circle, center not the origin, you would need the center and 1 point on the circumference. If you were asked to find the equation of a circle, center the origin, you only need 1 point on the circumference. So really, it's much easier to find the equation of a circle, center the origin. So let's see what we do. What do we know about a diameter? Well, a diameter is a line drawn through the center of the circle. And we know it divides the circle up into 2 half circles. So if we look over here, we know that this would be a semicircle, and we know that this would be a semicircle. So we know that on this line somewhere here, we must have the center. Now, obviously, if it's going to lie on the diameter, we know that a diameter is equal to 2 lots of radii. So looking at it like this is my center. This would be a radius, and this would be a radius. So actually, what I'm asking you to do here is to find the midpoint of that diameter, which of course is using our grade 11 theory. So let's go across and remind ourselves about that. Let's just remove that. Well, to get the center, we would say the center C, let's call it that, can be found by using the x of A added to the x of B, divide by 2, the y of A plus the y of B, divide by 2. Of course, your formula in your formula sheet will show as x1 plus x2, y1 plus y2, and all I've done is make it specific for this drawing by giving little subscripts A and B. So C's coordinate would be minus 2 plus 4, divide by 2, and this one would be 3 minus 7, divide by 2. So C's coordinate would be, that would give me 2 over 2, and this would give me minus 4 over 2, which means C's coordinate would be 1, negative 2. So we now know that this is going to be about here, coordinate 1, negative 2. I'd like to stress at this point that with analytical geometry, or if you want to call it coordinate geometry, it is always best to work with a diagram. And wherever possible, to fill in on the diagram what you find, because it always helps you structure your thinking and also sometimes helps you with later questions. So it just makes your life a little bit easier. So let's go back to the question again and see how this progresses. So right, we now have the center. So that means if I go to this equation, x minus a all squared added to y minus b all squared equals radius squared. I already know that this part here can be filled in with minus 1 plus 2. Remember, we discussed that this has a different sign to that there to get your center point. Right, so now we're going to substitute a point in. And we can choose to put this point in or that point in. I think I'm going to use this one because it's got smaller numbers, less work. So it's minus 2, 3, and I'm going to substitute into the equation. So right, here we go. And in place of x, I'm going to put minus 2 plus, and in place of y, I'm going to put 3. Now notice I've deliberately left the original center point in the pink so that you can remember what I'm doing here. So now this becomes minus 3 squared. Minus 3 squared, let's write the step rather than miss it. Minus 3 squared plus 5 squared equals r squared. So minus 3 squared is 9 plus 25 is equal to r squared. So that's very good news because now we know that r squared is equal to 34, which means at this stage we can write down the final equation. It's x minus 1 squared plus y plus 2 all squared equals 34. And that's well worth knowing because obviously if they're going to now carry on with the question, you have to know this equation. Now, the other thing you must be aware of is if you do make a mistake and you get the wrong equation, but you then carry on using your wrong equation to carry on the question, they will have to mark through. So that's always good to know. So even if you think, hang on, this thing I've got isn't quite, I don't feel comfortable with it as an answer, you can either go back and check if you've got time, or you can be assured that they are going to carry on marking with it. What a lot of the time the examiners do is they use the thing and they get you to do the first part and then they say, right, if the equation is, and they give you the equation in the next question, so that you're able to work on with the right equation, because sometimes it complicates your working. Right, so let's see what question B says. Okay, I think we'll put this equation in here. X minus 1 squared plus y plus 2 squared equals 34. It now says determine the equation of a tangent to the circle at A. Now we go over here and we look at the drawing and there is no tangent drawn in. Well, that's absolutely no problem. We put our own tangent in. Okay, so there it is, it's in. And they want me to find this equation. Now, I don't know if you remember the very first thing I talked to you about. I talked to you about the fact that we know from our paper 3 Euclidean geometry, which unfortunately we do need to know in this section, even though it's in paper 3. All we have to know is that the radius is always perpendicular to the tangent. Now, we are in a position to find the gradient of the radius, or if we like, the gradient of the diameter. Because in actual fact, the gradient of the radius would be the gradient of the diameter. So let's have a look how we do this. I'm just going to clear some space here so we can refer to it as we work. I like to have the drawing at hand. It just makes our lives a little bit easier. Right, so let's go back here. And as I've said to you, we need to get the gradient of the radius, or if you like, the diameter. Now, these 3 points are collinear. Do you remember when we did the revision of our grade 11 work, we talked about collinear, and basically what that means is all 3 points lie on the same line. So whatever 2 points I choose to use will give me the correct gradient. Now in this case, it looks to me as if using the center point and the point A, it would be the easiest 2 to use. So let's do that. So A's coordinate is minus 2, 3. And the center, which I've called C, is the coordinate 1, negative 2. So the gradient of the radius would be 3 minus 2 over minus 2 minus 1. That's using the formula y2 minus y1 over x2 minus x1. One of the big mistakes that I've noticed when marking scripts is that people are inclined to put the x on top of the y. So just be careful of that and avoid it if possible. Right, so here we are. It's 3 plus 2 over minus 3, which means my gradient is 5 over minus 3. Now, you'll remember that I said to you that we know this is a right angle. So it's always a good idea to put that in on the drawing so you won't forget. And now we need the gradient of the tangent. Now we know that if we multiply them, we've got to get negative 1. The easy way to do it is to tip this one upside down. And if this was a minus, make this one a plus. Now if you check and you take 5 over minus 3 times 3 over 5, you will see that you get the answer minus 1, which is exactly the outcome we wanted to have. Okay, so that's how we work with it. Now at this stage, knowing our gradient, which is 3/5, and the coordinates of A, which I'm just going to go back for up here, negative 2, 3, we can use some of our grade 11 work to help us out. I'm sure you remember last time I talked about y equals mx plus c, and the equation y minus y1 equals gradient x minus x1. I personally feel very strongly about the second formula that I've put all the ticks on, because in actual fact that formula gets you the equation immediately. But there's really nothing wrong with using the first way or the second way, and I'll do both just for the purpose of explanation. But in future, when we're finding tangents, I will stick to the second way. So let's have a look at this first way. We would go to y equals, and we would go and we would put in this gradient of 3/5 x plus c. We would then substitute in the point A with coordinate minus 2, 3. So that would make us have y equals 3/5. We're getting a nice multicolored equation here. Sorry, I just realized I didn't do the substitution. So back here we go. So we replace the y with 3, and we replace the x with minus 2, and we know that the c is what we're trying to solve for. So at this moment, the only unknown is c, which means we can actually find it. So we're going to go 3 is equal to minus 6 over 5 plus c, and so our c is equal to 3 plus 6 over 5, and of course our calculator fraction button can do that for us, but today I'm feeling very good. I'm going to do it mentally. 1 goes into there 5 times, 5 3s are 15 plus 6, which is going to give me 21 over 5. So your equation is y equals 3/5 x plus 21 over 5. Right, not such a pretty sight. If we wanted to, we could times it through by 5 and make it look a little nicer, flatter and simpler. But both of those are perfectly acceptable answers, and it would be your choice. So right, now in the light of that, let's see if the other method is perhaps an easier way to come up with this equation. So let's page up again. There we have it. So I'm saying to you, let's rather go y minus y1 equals the gradient, which is 3/5 x plus 2, because it's minus minus 2. So now I have y minus 3 equals 3/5 x plus 6/5. And just for convenience, it's times through by 5. So 5y minus 15 equals 3x plus 6, which means 5y equals 3x plus 6 plus 15, which means 5y equals 3x plus 21. And you can see we've come up with the same equation, just so much easier. So here we have it. And if we wanted to write it in pure y form, we would just divide through by the 5 again. So it's not a big problem either way. So really it's your personal preference. They both give us exactly the same answer, and it's very much a personal choice. So again, it's up to you. It depends what type of person you are. If you're the kind of person who's likely to forget to put equations together, stick to the second method. If you're someone who rather would stick to earlier teachings, grade 9 work and that sort of stuff, then stick to the first method. It's really not a problem which one you choose to do. Right, moving on to the next question. Right, now you can see in this question 3, we've been given a diagram and we're told that the circle, center C, is defined by this equation. And I can hear you laughing to yourself and saying, yes, they keep on asking that kind of question. Yes, they do. And so, yes, we do need to know how to complete the square always to find the equation of that circle. We're going to do that right now, but first of all, let's read the rest of the question. It says the equation of the line DE is defined by this equation. So straight away, I would write on it 5y minus 2x minus 13 equals 0. And of course, I'm now going to work with this equation in the next question, which you can almost guess as we page down. Yes, it says determine the coordinates of the center of the circle. So it's exactly what we anticipated was going to happen. So, right, let's see if we've got some room down the bottom here. No, I think let's rather work up the top. We want to find the center of the circle, which means we are going to complete the square on this. So we're going to go x squared plus 3x, leave a space, plus y squared minus 4y, leave a space, equals 1. Now I'm going to use the method I like. You're very welcome to use the other method. It's whatever you are comfortable with. So right, looking at this, we said ourselves, let's take the coefficient of x, which is 3. Half of that is 3 over 2. Squared is going to be 9 over 4. We can't just put it in here. We have to counteract it by balancing it and putting it that side. Now we go over here. The coefficient of y is minus 4. Half of minus 4 is minus 2. Squared is going to be plus 4. And we're going to add it on both sides because, again, it wasn't there before. We need to balance it out. So, right, now we know that this first part is going to become x. Remember, we take the square root of that, the square root of this one, and the sine of the middle one. So that gives me that. So square root, sine. Plus this next one, same story, square root of that, and this sine, which then gives me, and if we add that up, we're going to get 5, which is actually 29 quarters. Okay, perhaps just check me, but I'm pretty sure that's right. Okay, so now we know what the center of this, what the equation of the circle looks like in its other form. I'm going to write it in here because I'm sure it'll come in handy in later questions. So that's what we've got. It's y minus 2 all squared equals 29 over 4. Right, now, what was the actual question? Before we move there, let's just clear the space off. So we've got room to move and work. And the actual question said, determine the coordinates of the center of the circle. Well, that's going to be absolutely no problem now, isn't that so? Because we know that if we're looking over here, the center would be minus 3 over 2, 2. And a very good idea is once we've established that, is we write it in over here as well. So it's minus 3 over 2, 2. Just so that we don't have to go looking through our work to find out what is going on. We will know by just looking at our drawing what we already know. So it's always better to put it in on the drawing. Right, now the next question says to me, calculate the length of the diameter of the circle. Now, I'm sure you remember from the previous question, the diameter is twice the radius. Do we know the radius? Yes, we do. We've just completed the square, and we know from completing the square that this thing over here is the radius squared. So therefore, we know that the radius would equal the square root of that. So it would be the root of 29 over 2. And therefore, the diameter would be root 29 over 2 times 2. In other words, root 29. Now, you might say to me, don't we have to take out our calculators? The answer is clearly no. Remember that a square root, or surd, as we're writing it there, is a non-terminating, non-recurring decimal. And so if you take out your calculator, you are giving me an estimation of that answer, which is a problematic, unless you write there. It is 5 comma whatever, whatever, to so many decimal places. So rather don't go there. Rather leave it as a surd. Sometimes they're kind and they'll say in the question, this must be written in surd form, in which case you have no problem. Right, let's move on to the next question. It now says, determine the equation of the tangent. Now, we definitely need to know that, so let's go up there and see what we know. Now we do know we could work out the gradient of this radius just using those 2 points. But you agree with me that we've actually got another way we can find that gradient. We know that the diameter is perpendicular to the tangent. And we know the equation of that diameter. They gave it to me right in the beginning. So if I go over here and I take this 5y minus 2x minus 13 equals 0, and I work it into y form, I could say 5y is equal to 2x plus 13, which means y is equal to 2/5 x plus 13/5. Now that means that the gradient of this line is 2/5, which means the gradient of my tangent must be what? Well, it must clearly be minus 5/2. Remember, the object of the exercise is those two gradients multiplied together must give me minus 1. And so the easy shortcut for that is just to take it, invert it, and change its sign, because that would make sure that it multiplies to -1. Right, so let's go here. We now know the gradient, and we know the points of contact. So we have no problem at all at this stage in finding this equation. I'm going to use my favorite equation, which is this one. But as I've said, you're welcome to use the other one. So it's y minus 3 equals, the gradient is minus 5/2, x minus 3. Now, just because I don't like working with fractions much, and I know you don't either, let's times both sides by 2. So we're going to get 2y minus 6 equals, and this 2 is now gone, so it's minus 5x plus 15. That means that 2y is equal to minus 5x, and this is going to be 15 plus 6, which is 21. So we now have this equation, which I think I'm going to put in with black here. It's going to be 2y equals minus 5x plus 21. All right, so let's go down to the question again. It now says, write down. Now notice the instruction, write down. If it said calculate or evaluate or work out, you'd know there's something else, but this says write down. No lengthy calculations, and look at the mark allocation. So they don't want you to work too hard. They want you to actually find this actually quite easily. So let's go back there. We want the coordinates of D. Now, of course, we have got a long way of doing this. We could say D is a point of intersection of the diameter and the circle. And so I could do it by solving simultaneously for that point. But you agree with me that that would be worth more like 6 to 8 marks than 3 marks. So there has to be a better way of doing it. Now, of course, we were told this was a diameter. Now, if it's a diameter, we did discuss in the previous question that if we know the center, and we've got this, that this length equals this length. And of course, we could use distance form, but that would also be a huge production. It would take you quite a while to come up with an answer there. So let's rather look at it this way. We know this coordinate is 1, 3. And we know that this coordinate is minus 3/2, 2. So to find that D would be no problem if we use our midpoint formula. But of course, as you saw in the revision of our analytical, this would be like a kind of reverse use of it. Because we know C's coordinate, and we know we would find it by taking the x of D, which we don't know, and adding it to the x of E, which we do know, dividing by 2. And then we would take the y of D, which we don't know, adding it to the y of E, which would be 3, dividing by 2. And we know that the answer we get must be this. So at this stage, I can say, therefore, x plus 1/2 would have to give me the answer minus 3/2. And on the other hand, let's just clear space over here. I know that y plus 3 divided by 2 would have to equal this y value, which is 2. Now, starting over here, we can say let's times both sides by 2. So x plus 1 is equal to minus 3, which means x is equal to minus 3 minus 1, or if you like, x is minus 4. So we already know that this x value is minus 4. Here we've got y plus 3 equals 4, because we times both sides by 2 as well. And that means that y is equal to 4 minus 3, or if you like, y is equal to 1. So that's the coordinate 1. Just by the way, I have been a little bit remiss in not writing the questions down as we go. I've been doing them on the drawing, which is very useful. But if a question is asked, you have to provide the answer in the actual script as such, not only on your drawing. So let's go down there and fix that up. We're saying minus 4, 1 is the coordinate we got. So let's just bring that right down. So D's coordinate is minus 4, 1. And the equation of the tangent, let's also go and get that and put it where it should be. It was 2y equals minus 5x plus 21. 2y equals minus 5x plus 21. And so that would be the end of the question as such. And we can see that we are going to now be able to move on to the next one. Right, so I did leave a blank page here because I was going to turn over, but I decided not to, rather to keep it there. So now we're going to the next question, question 4. This one says the equation of a circle with radius 5 root 3 units is given by this. Ah, but you say we've done that before. Yes, we have. But the difference here is this time we don't have the full equation. If you look at it, we've got a p here. We do know the radius, so there has to be some tie in here. Now it says rewrite the equation in the form x minus a all squared plus y minus b all squared equals r squared. So let's do that first of all. So x squared plus y squared minus 10x plus 8y minus p equals 0. So let's get some space. We're going to say x squared minus 10x, leave a space, plus y squared plus 8y, leave a space, equals p. So all I've done now is reorganize how I'm writing the equation. I'm ready now to actually complete the square. Now, as I said to you earlier on, if you had had a number in front of your x squared and your y squared, all you would have done is divided through by it, because it would have had to be the same number. So if it was a 2x squared and a 2y squared, all's well. But if it was a 2x squared and a 3y squared, then it wouldn't be a circle anymore. It would actually be an ellipse. However, those are not in your syllabus, so not to worry about. But you do need to know that that's not a problem. So let's go here and do this question. So we take the coefficient of x, which is minus 10. We halve it, which is minus 5. We square it, which is 25. We put a 25 on each side. Then we take the coefficient of y, which is 8. Halve it is 4. Square it is 16. Add it to both sides. Right, so at this stage we can go x minus 5 all squared, y plus 4 all squared equals p plus, and if we add those numbers, we're going to get 41. So we've written it in the right form. Now it says, hence calculate the value of p. Well, this is where the other bit of information is going to come in handy. They told me that the radius of this circle is 5 root 3. And we know that if this was 5 root 3, we would have had to square it to get what went in the formula. So squaring that, you'd square the first one, and then you'd square this guy, which is going to give you 3, so it would be 75. So in actual fact, we know that that would have been 75. So at this stage now, I know that p plus 41 is equal to 75. So let's page down, and now it's easy enough to solve. So p is equal to 75 minus 41, and if we subtract that, we're going to get 4, and that's going to be 75, so it's going to be 34. And so we have our p-value, and we have it written in the correct form, which were the two parts of the question. That's a good idea to put it in a block so it makes it a bit more distinguished between the various questions. Right, so that was relatively easy, and it's quite interesting. Now what we're going to do is we're going to stop for a few seconds and have a look at some old work from last year, namely your transformation and your translations, your enlargements, your rotations. We're going to do a quick summary of those before we move to the next question. The good news is that analytical geometry lends itself to using that kind of stuff. So let's go across now and do a quick summary. You won't be getting to use all of the things I'm going to show you now, but it's a good thing to keep in mind for future work. So let's get ourselves our blank page, and let's call this transformations. Now, the first kind we get is what we call a translation. And basically, all that is if we've got a Cartesian plane and we stick a coordinate in over here, say, we can reposition it by telling the coordinate what to do. So, for example, if I've got x, y, I could say to you, make it x plus 1, y minus 7. So what you would do is you'd say, okay, whatever this coordinate was, let's make it minus 3, 2. They're telling me take A, which is minus 3, 2. And now the new point will become minus 3 plus 1, which is minus 2, and 2 minus 7, which is minus 5. And that would be my A dash, if you like. And so I would say, right, that would be minus 2, minus 5, and that would be A dash. So what am I saying to you? I'm saying to you, move 1 unit and then 7 units down. That's what we call a translation. Okay, let's look at the next one. The second set are known as reflections. Now, reflections, we have reflections in the x-axis, reflections in the y-axis, and reflections in the line y equals x. Right, so if we go here and we put a Cartesian plane up quickly, let's put up 3 of them just so we can discuss each one. And we take any coordinate really, it doesn't really matter which one, but let's take something that's going to be easy to see. So let's take A and let's call it the coordinate 5, 1. And I want a reflection in the x-axis. Well, we know then that this is where we are going to fold, if you like, and effectively push it down here. So if I look at this new point, what has happened? Well, certainly you can see that the x value has not changed. But the y value has changed. It's gone from plus 1 to minus 1. And so the rule we would use here is we would say for this particular one, x, y will become the coordinate x minus y. Now, my advice to you is if you ever get stuck, just use the drawings like I'm doing to sort them out. But they're relatively easy to remember, and mostly we find that this section's a section that you perform on very well and do very nicely on. Right, now let's go here. Let's use the same coordinate, A, coordinate 5, 1. And what I want to do now is I want to reflect it about the y-axis. So there's the y-axis. If I'm going to reflect it about y-axis, it's going to head this side. Now, what do you know about this coordinate? Well, you can see that the y value is staying the same, but the x value is clearly changing to a minus 5. If you fold it on that line, I'm sure you'll be able to see that those two would coincide. Right, so now let's go and have a look at the rule for that then. Well, the rule for that would tell me that xy becomes minus xy. Okay, and now we go to this one here, and this one we're reflecting about the line y equals x. So I'm going to put it in pink so we can refer to it. And again, let's use that same coordinate. It's quite a nice coordinate. It's very distinctly on one side of the story. So that's the coordinate 5, 1. Now, if we're going to reflect around this line, I'm sure you can see that we are going to bring it up here somewhere. And if that's the case, do you agree with me that we couldn't have an x value of 5? So actually what happens is these turn around. So you can see that this one's rule says that the coordinate xy is going to change to yx. Now you are going to meet this particular reflection in a completely different section. When we go to work on functions for this year, we're going to work with inverses. And you're going to find that an inverse is basically a simple reflection about the line y equals x. So it actually makes it very, very easy for you to work with. It's not really such a new section in the sense that you're just doing reflections. But we will spend at least a whole hour on these things in a later stage. But for now, just know that we're reflecting about the line y equals x. Right, the next lot are called rotations. Now, in grade 12, we get a much more complicated form of rotation. In grade 11, we've done them very basically. We've worked with 90 degrees clockwise and anti-clockwise, 270 clockwise and anti-clockwise, and 180 clockwise or anti-clockwise. But in matric, you're going to work with rotations of 30 or maybe 45 degrees or even 10 degrees. It really doesn't matter what size angle I choose. But we are not going to handle this today because our topic is actually analytical, and mostly we're going to work with the traditional ones. So for now, we're going to work with this. In the later stage, I will pull in a whole lot of work after we've finalized our compound angles, and I'll show you how that actually works with these other rotations. So, okay, let's talk about these traditional ones. Let's talk about 90 degrees anti-clockwise. Now, what I'm going to do is give you the rule, and then I'll show you on the drawing how we come up with this rule. So, basically, xy will become minus yx. 90 degrees clockwise, well, that means the rule would be xy becomes y minus x. Then we have 180 degrees, and there it doesn't matter whether I go anti-clockwise or clockwise. We'll talk about that in a moment. The rule will be xy becomes minus x minus y. And then, of course, we've got 270 degrees anti-clockwise, which uses the rule xy becomes y minus x. And then we have 270 degrees clockwise, where the rule says xy becomes minus yx. Now, at the moment, I know what you're saying. You're saying, hang on a moment, look over here, that is the same as that, and this one is the same as this one. Yes, it is. Now, let's talk about y. Okay, let's go to that drawing I promised you. And let's put in my favorite point, coordinate A with coordinate 5, 1. Now, I'm going to put in a line here, and hopefully this will work, but we'll see if it does or doesn't. And what I'm going to do now is I'm going to show you what happens. In fact, let's first clone it, because I think it's good to have an extra one there. So let's clone it, and let's put it on top of the other one. So when I pull it, it'll leave the other one behind. Right, so now what is going to happen is I'm going to move this other ray, I hope, around, showing you what's happening. Now, if I'm talking about 90 degrees anti-clockwise, I'm going to go over here, pick up one of these lines, and I'm going to pull it around to there. Okay, and I think you can see this is more or less 90 degrees anti-clockwise. Now, if you look at it, you can see that the x value would definitely not be 5 positioned where it is. It must be 1, and in fact, it must be minus 1. And this y value, because that line has maintained its length, will become 5. And of course, that demonstrates that example. Now, if I measured this in a clockwise direction, do you agree with me this would be 270 degrees clockwise, and this is 90 degrees anti-clockwise. So that's why I'm saying that that will give you exactly the same rule, which is quite useful to know. So let's move on now, and let's look at the other one, and I'm going to clear the drawing up a little bit because I want to just demonstrate the other version. But you can see how nicely this works. I'm pleased to say. I was wondering if it was going to pull both lines, but it didn't. Right, now if I'm taking 90 degrees clockwise, there you can see that more or less looks like 90 degrees. And you can now see that if I'm going to put this coordinate in here, this must be 1 with a negative 5, which then supports that rule that we have up there. Now, of course, again, if this is 90 degrees clockwise, this must be 270 degrees anti-clockwise. And as a result, you can see the rule is the same. So we don't have to worry with that. All right, let's clear the drawing up one more time to show you the last one, which is where we talk about 180 degrees. Now there we are. If I go 180 degrees like this, or I go 180 degrees like that, does it make any difference at all to my positioning? And the answer is clearly no. You can see it came to the same position. So my A dashed in this case would be minus 5 minus 1. You can see that the x value is longer than the y value, so it makes perfect sense. So right, that takes care of our rotations for now. As I say, there is a little bit more in your grade 12 syllabus, which we will handle at a later stage. Right, now moving on to the last thing, which is the enlargements. Now basically what this involves is if we have a point x, y, we can enlarge by a factor of k or reduce by a factor of k by multiplying the coordinates by that k. Now what is interesting about this is that in actual fact, this will change the relationship between its perimeter. All these other transformations have not affected the actual size of the figure we're working with. So if I had a triangle and I was translating it, it would be the same triangle translated. If I had a triangle and I rotate it, it's the same triangle rotated. If it's a triangle and I'm reflecting it, it's the same triangle reflected. However, as soon as I deal with enlargements or reductions, it does affect the shape or the rigidity of the actual figure. So let's have a look at what I'm talking about. Let's suppose, since we're working with circles, let's put a circle on here. And let's make it over there. Now, if that is my circle, and let's put a center in on it, over there, if I start enlarging, do you agree with me that in actual fact, I must be careful how I enlarge it, so let's just do that and then reposition it. It would change the perimeter, it would change the area, it would alter how it looks. And if I reduced it similarly, so I brought it to a tiny little circle, let me just bring it back to the center. You can see that obviously the perimeter has changed and the area has changed. So you can see that that would cause a little complication. Now, all we need to remember with this is that if we are dealing with the perimeter of a figure and the original has a value of star, and we've scaled by a factor k, then the new perimeter will be k star, whatever that star might be. So I might have said to you, the perimeter of your original one was 7, and our scale factor is 2. Then you'll be able to tell me that the perimeter of the new one is going to be 2 times 7, or 14. So that is how perimeter works. So let's look at area then. If we're talking about area and a scale factor of k still, and let's say the original has a value of squish, then the new one, new area, is k squared squish. So the area compounds it twice. Now let's make it more sense for you. Do you agree if I take a little rectangle like this and I say that's 4 and I say that's 2, and I say what is its perimeter? Well, it's a rectangle, so we would know that that's 4 and that's 2, so the perimeter would be 4 plus 2 plus 4 plus 2, so it would be 12. Now if I scale it upwards by a factor of 2, this is now 4 and this is now 8, 4 and 8, and of course we know this, so now we're going to add these up. So it's 4 and 8, 4 and 8, so it's going to be 24. Do you agree with me that the perimeter increased by a multiple of 2? So we're quite clear that that works for perimeter. So let's see now if we use the area of this particular drawing I've drawn, if that's still true, that it would be 4 times the previous area. So let's get a bit of space. So the area of the original would have been 4 times 2, which is 8. And the area of the new one would be 4 times 8, which is, 32. I nearly wrote perimeter instead of area. Okay, let's just put it there. So the area would be 4 times 8, which is 32. Now you can see that if you look there, that's times by 4. And isn't 4 actually 2 squared, which was the scale factor 2 squared? So it all makes perfect sense. Now, I'm not going into more detail than that, but I think it's given you a very good basis of what you did in grade 11 and how we're going to use it in the next question will come up. And we'll be able to discuss it a little bit more. So let's go to the next question. Right, we'll see here, it says refer to the diagram. Given the circle's equation, and look at that, miracles of miracles, they've actually given me this equation in the form of x minus a all squared plus y minus b all squared equals r squared. So not every question expects you to complete the square. Right, so now we're going to go over here, and we're going to say, well, what does that tell me? That tells me immediately that this coordinate is 2, 2. And what does it tell me about the radius? It tells me the radius is 2, because remember that's radius squared, so therefore radius is 2. Right, so let's go to what they want me to do. First question, they say write down the coordinates of A, B, and C. So I've already found C. C is absolutely no problem. Let's put it in a different color so it stands out. C is the coordinate 2, 2. Now, this is where tangents come into things. Remember we discussed that a tangent is at right angles to the radius. Now, do you agree with me, looking at that picture, that the tangent is actually the x and the y axis? Now, this can be very useful in a lot of different cases. So if we go over here, we can see that if we draw down the radius here, that would be a right angle. So we know that this value here would have to have the same x value. And of course, because it's on the axis, I know that that would have to be 0. Likewise, if I put this one in, this one will have the same y value. And obviously, because it's on the axis, that's 0. So A and B are not going to be problematic. A is the coordinate 0, 2, and B is the coordinate 2, 0. Okay, nice little start to the question. Right, now it says, the circle is transformed. Great, so remember I warned you that it's more than likely that if they're going to ask transformations, analytical is a really nice place to put it in. Well, here we go. So let's see what it does. It says it's transformed using that rule. Write down the coordinates of the center and the length of the radius. Now, what did I say to you about translation, reflection, and rotation? I said to you the shape is preserved. In other words, is the radius likely to change? And actually, it's not going to change. It's only going to change if I start enlarging or reducing the circle. So I know already what my radius will be. I know that my radius would be 2. However, the center will certainly change. My center was 2, 2. And if I'm going to use this transformation, it's going to be x plus 2, so it'll be now 4, and y plus 2, which will be 4 as well. So now they want the coordinates of the center, so the center is 4, 4. Now, in actual fact, if we look at this, we can see that we can now write down the equation. We could say it's x minus 4 all squared added to y minus 4 all squared equals radius squared. And quite honestly, I don't like to write it like that, but maybe it's not a bad idea. So what I would do is I'd write it like this. However, they didn't ask me to find that equation, so the fact that I worked it out is not problematic. Right, now let's turn over. I've actually replicated the question over here, and let's add in the bits we know already. We know that that was 2, 2. We know that this coordinate was 0, 2, and this coordinate was 2, 0. And let's read what the rest of the question is asking. It says, given this circle, the original circle goes through an enlargement of factor k. So in other words, they're leaving the factor unknown. So scale factor k. And they say produces a center for the new circle of coordinate 6, 6. Now the original circle had a center 2, 2. So what can we conclude by looking at that? Well, let's see what they actually want us to do. They want me to, they said the original circle goes through an enlargement of factor k and produces a center for the new circle of coordinates, whatever. Write down the value of k. So yes, that's exactly what they want me to do. They want me to look at this and say, what would the scale factor have been for that to happen? Well, it's clear that if I've gone from 2, 2 to 6, 6, I've literally multiplied the x and the y coordinate by 3. So So if we look over here, we can say this was 2, 2, and it became 3 times 2, 3 times 2, and therefore the scale factor is k equals 3. Right, what else do they ask me? So we know k is equal to 3. Right, the next part of the question says, will the x and y axes still be tangents to the new circle? Motivate your answer. That's an interesting question. We have to sort of think about this, and we have to decide whether, or what is this enlargement going to do to things? Well, let's go back to the drawing and let's sort of get ourselves positioned. So do you agree with me that if I'm going to the coordinate 6, 6, sort of would be out here somewhere? Now, if that is so, and the radius was 2 in the original, remember what I said to you about an enlargement does not preserve the shape, it preserves the shape, but it doesn't keep the figure rigid. It actually is going to slide it and move it in and out like I showed you with the circle earlier. So therefore, we can actually know for a fact that our radius 2 has changed. So our radius must also be affected by the scale factor 3. So if we do that, the radius is 6. So now if the radius is 6, can you see that there would be a point over here with coordinates 0, 6, and a point down here with coordinates 6, 0. And so my new circle, which I'm going to actually put in here on top of this one, and let's hope I can manage to get a reasonably decent circle here. I will just maneuver it around till it looks reasonable. Okay, it doesn't like going to the top, so let's not worry putting that in then. It's going to be a little bit confusing otherwise. Let's cut it out. Right, so going down here then, motivate your answer. Well, that's easy enough to do. You could say, I know that the radius will now be 6, as it has factors, it has factored by 3. Therefore, tangent at 0, 6 and 6, 0. And that's enough because it's only 2 marks that they're asking for here. Right, now it says write down the equation of the new circle. Well, we know what its centre is. It's x minus 6 squared added to y minus 6 squared, and that is equal to the radius squared. Now we know that the radius changed to 6, so radius squared would be 36. There's nothing wrong with writing 6 squared, but I actually quite like it like that. Right, so we have got that picture, that particular question done. So let's now move to the next one and see what happens. But I think it's quite an interesting question, this, because it's actually got you to the point where you've realized we can mix various sections together, and that's always good. And of course, it's every maths teacher's dream to find questions that involve more than one section. Right, moving to the next question. It says a circle with center T and equation this, and a circle with center S and this equation are given. Use analytical methods to show that the circles touch each other. Oh my goodness, what are they on about now? Well, actually what it means is the following. They want me to find, or show rather, that if I have a circle and another circle of various sizes, and that looks almost like an ellipse rather than a circle, so let's just see if we can rectify it a little bit, make it look a little bit more circular. Okay, it doesn't really matter. They want me to show that in fact this is what happens, that they touch each other, and they've given me both equations. But of course, as we know, this is a golden opportunity for us to get you to complete the square. So let's do that first of all. Right, so over here we have x squared plus y squared minus 16x minus 20y plus 115. And we want to complete the square. We don't need to do this one. This one we already know that our center would be minus 4, 5, and our radius would be 6. Both very useful bits of information, as you'll see later on. Now this one here we need to complete the square, so I'm going to actually clear this away, and we are going to use the space for that, and then later on I'll go and put it on a new drawing. Right, so now let's complete the square on this. By now we're becoming experts, I'm sure, and we don't even have to worry about this too much. We know we're going to go x squared minus 16x, And then we're going to go y squared minus 20y equals minus 115. And now we're going to say, right, let's take the coefficient of the x, which is minus 16, halve it, it's 8, minus 8, square it, it's 64. We add 64 both sides. Right, now we take the coefficient of y, which is minus 20, half of it is minus 10, square it, we get 100, add 100 both sides. So right, we are ready now to say that that will be x minus 8 all squared added to y minus 10 all squared equals, and if we subtract, or add this lot up anyhow, 100 from minus 115 is minus 15 from 64. I should just pull the calculator up, but I'm trying to be a good example here and use my brains, and I'm going to get 49. Right, so now I know that this circle could rather have been written as x minus 8 all squared plus y minus 10 all squared equals 49, which is good news because I know the center is going to be 8, 10, and the radius is going to be 7. Now remember I said to you these are important bits of information, and I'm sure at this moment in time you're looking at it and saying, really, I'm not really sure this is so important, but let's show you why I think it is important. Let's just find a bit of blank space here, and let's put a Cartesian plane up, and let's plot a sort of rough sketch. Remember I said to you it's always a good idea, if possible, to have a picture. So minus 4, 5 about here, and we want a radius of 6 over there somewhere, and the other one we have 8, 10, and a radius of 7. So over here we have 8, 10, and a radius of 7. Now, ultimately we want to show, lovely circles these, they look almost like eggs, but it's fine, we can use our imagination here. I want to show that this actually happens. So how on earth am I going to do that? Well, remember I said to you a very important part was also here, and the very important part is the fact that this radius is 6 and this radius is 7. Now, if I can show that the distance between these 2 points give me 13, then in actual fact these had to touch. If, however, the distances between them was less than 13, it would mean that the circles overlapped like this, and if it was more than 13, it would mean the circles were doing that. So let's go and see whether it's true or not. So here we have it, and we're going to work out the distance between these centers. So distance squared is equal to x2 minus x1 all squared added to y2 minus y1 all squared, which is minus 12 squared, which is 144, and this is going to be minus 5 squared, which is 25, which means I'm going to get 169, which means my distance is actually 13. Now, that's very good news because this here is made up of 6 and this here is made up of 7, and 6 plus 7 makes 13. So the only way for this distance to have been 13 is for those 2 circles to have touched. As I say over here, if that had been the case, and this was 7 and this was 6, you can see that this distance would have been far greater than 13. And over here, if this was 6 and over here this was 7, let's put it in a different color, then you can see that this distance would have been less than 13. So it's a very valuable thing to know and appreciate. Let's have a look now at the next question, and you can see that this is now sort of coming together as a really nice cohesive section. Determine the length of the tangent from the point 8, negative 1 to the circle with center S. So the circle with center S is this bottom circle. So just for the purposes of this work, I'm going to take this one out so we can just work with a slightly less messy drawing. Okay, now they say the coordinate 8, negative 1. Can you clearly see that that 8, negative 1 will not be lying inside that circle, or indeed on the circumference? You can see quite clearly that that's way past 6 units away. So right, let's get some more space over here. and let's work. Now, they want to know the distance. Now, this is a very, very popular question. The distance from here to the circle would be from here to there. Now, what do we know? The only thing we know is that this radius is 6. Do you agree with me that there wouldn't be a problem to find that distance? Because we know this coordinate and we know this coordinate, so we could take -4, 5, and the coordinate 8, -1, and we can find this distance here. Let's call this distance A. So A squared would equal -4 minus 8 all squared, added to 5 plus 1 all squared, which would make that -12 squared, which is 144, and this is 6 squared, which is 36. And if we add that, I think we get 180. So this is the root of 180. We know that that's 6. So now we have to find this guy. Now, what do we know? We know that the radius and the tangent are always at right angles to each other. And this little fact is going to come back in just about every question you do on this section. So that is a right angle over there. So we know that my favorite mathematician, Pythagoras, can be used here. So we know that if let's give this A, let's call this B, let's call that C. From Pythagoras, I know that A squared equals B squared plus C squared. And it's a good idea to tell your examiner that you are using Pythagoras' theorem. Now, A squared is going to be 180. B squared we don't know, that's what we're ultimately looking for. And the C squared is going to be 36. So that means that B squared is equal to 180 minus 36, which is very good news because that's going to be 144 is equal to B squared, which means B is equal to 12. So therefore, this distance here is going to be 12 units. So it's very easy. So if they ever ask you to find the distance between a point outside and a point of contact, you always revert to Pythagoras. Pythagoras always gets you out of trouble here. Right, let's see what the next question brings. Right, if the radius of the circle this is half the radius of the circle that, calculate the numerical value of A. Right, so again, it's like this feeling, oh my gosh, but not to worry. As you know, that if we are working with this, we will complete the square, and if we are working with this, we'll complete the square in order to be able to find that. So let's start with the first one. It's x squared minus 4x, leave a space, plus y squared plus 6y, leave a space, equals A. Now, completing the square, we take the coefficient of x, we halve it, and we square it. We add it to both sides. We take the coefficient of y, halve it, it's 3, square it, it's 9, add it to both sides. So this becomes x minus 2 all squared plus y plus 3 all squared equals A plus 13. Now, they're talking about the radius, so I'm not really interested in the center point, but I do know that the radius of this, remember this is r squared, will be the square root of A plus 13. Right, let's move to the other one. Again, we have to complete the square, and you can see it's not hugely different to what we've done already. So if we look here, we've got x squared minus 4x, leave a space, plus y squared plus 6y, leave a space, equals 3. And again, we're going to complete the square, so half of that is minus 2. Squared is going to be 4, added both sides. Half of that is 3, squared is going to be 9, added to both sides. So we're going to get x minus 2 all squared, added to y plus 3 all squared, equals 7 and 9 is 16. And so here I see my radius is actually 4. Again, radius squared being in this position, so the radius is 4. Now, at this stage, we go looking for the link between these two circles. And the link between these two circles is that this radius is half of this radius. So what is that telling me? Well, it's telling me that the root of A plus 13 has to equal 2. Since the radius of this one was 4, half of that would be 2, and that gives me an equation I can solve. So looking at this equation, I can square both sides to solve. Now remember, if we square both sides of an equation, or anything, square anything of this format, then there's always a possibility that we get an error. For example, we know that minus 2 is not equal to 2. But if I square this side and I square this side, it's now true. So you can see we have to take this into account. But let's carry on here first of all. So this is going to be a plus 13 equals 4. And so a is equal to minus 9. Now, because we squared, we would have to check back into the original, which is that one over there, to make sure this works. So minus 9 plus 13 would be the same as saying the square root of 4, which is the same as saying 2. And that's good news because that's what we know it has to equal. So this is a valid answer. Right, so you can see that this is really a very nice section. Lots of simple concepts that you've done before that have been pulled back in: your Pythagoras, your distance formula, your gradient, and of course your completing the square. Let's not forget that. And so it's really an enjoyable section, and it's a nice opportunity to do really, really well in this particular paper. It's paper 2, and it is an important part of paper 2. And yeah, I hope you've enjoyed being with us today, and I look forward to being with you next time. Thank you.